All right, so this next section, measuring voltage and current, we're going to talk about how we do these things. Now, we've already seen this in lab, especially with lab 7.9 and 7.10, but in that lab, or in those labs, we use what's called a multimeter. And a multimeter is a multimeter because it's multiple meters. It can measure current, it can measure voltage, and it can measure resistance. Now, current we know is measured in amps, and for that we use an ammeter. Voltage we know is measured in volts, and that is a voltmeter. And resistance is measured in ohms, and for that, I don't really have a special name for that, but that's just a way to measure resistance. So these three things are all tied into the multimeter. And now specifically, I want to talk just a little bit about how we measure voltage and current in circuits. So an ammeter, first off, an ammeter is a device that measures current. Because charge and current flows through circuit elements, an ammeter has to be placed in line or in series with the circuit elements whose current is being measured. And my analogy for this is always the same. If you're next to a stream, all right, you see this stream of water flowing, and you want to know the current of that water, how fast that current is flowing, the best way to do that is to jump into the water. You jump into the water, and that current carries you a certain distance in a certain amount of time. So current has to be measured in line with the circuit. So in the lab, we kind of, if we use the simulation, we kind of cheat because we have something that just does it for us, a little target thing. But in reality, if we measure current, we have to be in line with that circuit. So here, if I have my basic battery, 1.5 volts, and I have some resistance, if I want to get the resistance, I need to know what that current is that's flowing through the circuit. Because I know if this is the only resistor, I know that the voltage drop is 1.5 volts. But I don't know anything else about that circuit. So I can use Ohm's law to kind of fill in the gaps. But I need to get the current that's going through the circuit to understand one of the other things. Because I know that voltage is current times resistance, or resistance is voltage over the current. But I don't have resistance. All I have is voltage. So I need that other concept in order to figure it out. So I can place an ammeter, gets placed in series with that, and then the current passes through it, and as it's passing through it, it can know what that current is. So in order to do that, we assume that an ammeter has an internal resistance of 0 ohms. There's no internal resistance. So just by it being in series does not affect the equivalent resistance of the circuit. So if I have 1.5 volts, and now I know that it's 0.6 ohms, resistance is V over I, and I can do 1.5 divided by 0.6, and from those two things alone, I can determine that this is 2.5 ohms, and that's just using Ohm's law. So here we go. I have the current, I have the voltage, and I get 2.5 ohms. And again, we're assuming that this ammeter is ideal and that its internal resistance is 0. No ohms of internal resistance. And it just is, it's like you jumping into the water. You can feel how fast the water's flowing. Well, this isn't the flow of water. This is the flow of electrons. Because remember, current is just a charge passing in a given amount of time. So we can use a voltmeter to measure potential difference, or the voltage in a circuit. So because the potential difference is measured across a circuit element, we're looking to see what the voltage is initially and the voltage is finally. We can get that change in voltage. And again, our analogy for this is like gravitational potential energy. Voltage is electric potential energy. So across the battery, I gain 9 volts in electric potential energy. Across each of the resistors, I will lose 9 volts in electric potential energy. So if I want to figure out exactly what the voltage drop across R1 is and the voltage drop across R2, I need to know either the resistance and the current, or I can use this concept of Kirchhoff's loop law. So let's take a look at that. If I get the voltmeter and I put it across this resistor, I see that it has a voltage drop of 6 volts. Kirchhoff's loop law states that I have whatever this 9 minus this 6 volts is what's left on this voltage for the first resistor, and that's going to be 3 volts. Now with a voltmeter, we assume that it's not affecting the current of the circuit. It's not making a parallel branch, but it kind of is. So with a ammeter, we assume that the resistance was 0. Well, with a voltmeter, we assume that it's got an infinite resistance. So no current wants to go in this direction, but the voltmeter can see what the voltage is before the circuit, or before the resistor, and after the resistor. And that's what it does for us. So with that in mind, I know that this is 6 volts. I can do this a couple of different ways. I can say, all right, well, if that's 6 volts, that means this is 3 volts. And then I can say 3 volts. If I want to get the resistance, I know that the current is the same throughout this circuit. So I can take my 6 volt resistance, or the voltage drop of 6 volts across that resistor, divided by its current, which is 24 ohms. The resistance of 24 ohms, the current going through the branch is 0.25 amps. It's a quarter of an amp, which means that there also is 0.25 amps going through this resistor. So for that resistance, that voltage drop divided by the current gives me 12 ohms. And this also makes sense because this is 6 volts, this is 3 volts, half the voltage drop, half the resistance. And that's really about it for right now. So the only two things that we need to worry about is if I want to measure current. So here's my circuit. Very simple circuit with, let's give it 2 light bulbs here. If I want to know what the current is in that circuit, I need to break the circuit and I need to put an ammeter in that circuit, and that will read the current. All right, we assume that the ammeter has an internal resistance of 0 ohms. If I want to get the voltage drop, it's always the voltage drop across one of your components. So that means that I put the voltmeter has to be in parallel with that. And I could do one of these. I could do, both of these. If there were multiple, it doesn't matter. But I want to get it tells me my potential before and my potential after. So it'll give me the voltage drop across that component. And we assume that for a voltmeter, we assume that it's essentially infinite resistance. And that way it's not drawing any of the current to leave the circuit and go through the voltmeter instead of continuing to go straight across the light bulb as it continues. So that's it for current and voltage. The last thing we're going to do is we're going to combine the concept of series and the concept of parallel circuits, and we're going to make what's known as complex circuits. We're going to take a look at that in the next segment.